Okay, so this week we are doing the buffers experiment. This is the overview of what I'm going to be talking about today. Quickly, we are going to be going over what is a weak acid, very quickly what is a weak base, how to make a buffer, deriving the Henderson-Hasselbalch equation and how we can use that for buffers. Then I will be going through the experimental part on the board, not on the lecture. Okay, so what is a weak acid? Well, let's first think of what is a strong acid. So a strong acid like HCl, H2SO4, etc., when they dissociate one proton, or H+, the proton reacts with the water molecule to make hydronium and the conjugate base. In this case, it's Cl-. So when you have a strong acid reacting with water, it dissociates 100%. So all of the protons from HCl are going to be reacting with water to make hydronium ions. In the case of a weak acid, the weak acid does not dissociate 100%. It is going to reach an equilibrium between the acid and its conjugate base when it reacts with water. So the equilibrium constant for an acid, or Ka, is represented by the products, the concentration of the products. So one product is hydronium, one product is the conjugate base, A-, and our reactant in this case is HA. So just like every other equilibrium constant equation, it's products over reactants. Okay, so real quickly we can do the same thing with bases. So when bases are put in water, they are taking one of the hydrogens to become protonated to give off OH minuses. And its equilibrium constant looks similar to this one. It's called Kb, and it's products over reactant. Okay, so what is a buffer? Well, a buffer is a solution of weak acid that is able to resist a pH change. So when we get to the Henderson-Hasselbalch portion, we'll be able to see that when you have a buffer, the pH of that buffer equals the pKa, or the negative log of its equilibrium constant. So in a buffer, what happens is you have a weak acid in equilibrium at a certain concentration. And when you add either strong acid or strong base to that buffer system, so on this graph we have a titrant volume here, and the titrant is going to be either strong acid or strong base. And so what happens is when you add certain volumes of your titrant to the buffer system, the pH doesn't really change. And so that's what makes an effective buffer. And why would you want a buffer? So if you're doing a chemical reaction or a cellular experiment or something that is sensitive to a pH, you want to make sure to have a buffer system that will maintain that pH for you during your experiment. So at a certain point, however, when you start adding too much titrant, you are going to see a sharp increase of pH the equivalence point when your H pluses equal your OH minuses, and then you'll see it taper off. Okay, so today we have solutions of an unknown acid and its conjugate base, and we are going to be creating our own buffer. How do we do that? So a buffer is in equilibrium when your concentration of HA equals your concentration of conjugate base. So we are simply going to be adding identical volumes of a solution of HA and a solution of H minus, mixing them together. They're going to be at equilibrium. Okay. So, what happens when you start adding a titrant in? So, in this case, we have our equilibrium equation of HA reacting with H2O to make hydronium and A minus. This is a reversible reaction. So when we add H3O plus, we're going to be adding it on this side. So we are going to be doing the reverse reaction. So the reverse reaction is written here. H3O plus A minus gives you HA and water. Okay. And so for this example, we have a given Ka of 1 times 10 to the minus 8. We have our initial HA and A minus concentrations, and we're adding 0.01. So if we took the negative log of this Ka, we would see that our pKa is 8. So at equilibrium, the pH of that solution is also 8. We are adding 0.01 concentration of H3O plus. So what that means is if you took the negative log of H3O plus, which is the definition of pH, in this case we're adding a pH of 2 to a pH of 8. Okay, so we want to see experimentally what is going to happen. Okay, so we can predict what is going to happen based on our ICE table. So we know what our initial concentrations of these guys are. We are adding, so we're starting with 0.01 of H3O plus. We're starting with 0.1 of A minus and 0.1 of HA. We are reacting all of our H3O plus with our A minus. So we're subtracting these amounts because we're making HA. So we're adding to the HA column. So H3O plus is all reacted. We have 0.09 of A minus and 0.11 of HA. So we can plug these in here to solve for H3O plus. And what that H3O plus means is how much H3O plus we have at equilibrium. So when we started this reaction, we had H3O plus because these guys are in equilibrium. And then we added more. So now this number is different. Okay. So this number is our unknown. So we're going to represent it with just x. So if we set up this equation and solve for x, we get 1.2 times 10 to the minus 8. So that's our new total H3O plus at equilibrium. If we take the negative log of that, we get 7.9. So essentially what we did was we started with a buffer that had a pH of 8. We added a small concentration of something with a pH 2, and the pH remained relatively the same. So 7.9 is not much different than 8. So essentially, that's a good buffer system. If it wasn't a good buffer system, you would see a much larger change in pH here. So when we talk about the buffer capacity of something later, we're talking about how good is the buffer at retaining its pH. Alright. So, the Henderson-Hasselbalch equation directly relates pKa to pH using this equation here. So how do we get there? Well, we're going to start with our Ka equals our concentration equation, so our equilibrium constant. When you have logarithms, so there's a step missing here. Okay, so you might be thinking, how do you get from this to this minus this? Well, when you have the log of, essentially what we did was we took the negative log of all of this. When you have a log of something times something, you can rewrite it as the log of it's an addition transformation. So you can pull out the top part and add the log of that separately. But remember, this is all multiplied by -1. So it's this minus this. Email me if you have more questions on deriving logarithms, or look at a trigonometry textbook or pre-calculus. Okay, so we know that the negative log of H3O plus is pH. We know that the negative log of Ka is pKa. So we can subtract the negative log of this guy on both sides, or we can add the log of this guy on both sides to get pKa plus the log of A minus over HA equals pH. So this is our Henderson-Hasselbalch equation. So this essentially gives us the ability experimentally to measure pH. So when we have an unknown acid, we don't know what the acid is. We have known concentrations, so we know what concentrations of conjugate base and acid we have. We don't know what its pKa is because we don't know what the acid is, but we can measure its pH. So essentially what we are going to be doing today is creating a bunch of diluted concentrations of a buffer system, measuring its pH to find its pKa. Okay, so now we're going to switch to the board. Okay, so we're going to start with this board here. So the first step that we are going to be doing in today's experiment is making our buffer solutions. So we have solution A, which contains a 0.1 molar solution of HA. And we have solution B, which contains a 0.1 molar solution of A minus. We're going to be adding those together to make our first buffer. So the first thing we need to do is figure out, based on our initial concentrations of HA and A minus, we need to figure out what our new concentration is. So we need to multiply how much we're taking of our HA. So we're taking 0.05 liters or 50 mils, and its initial concentration is 0.1 molar. Okay, so we are essentially taking out 0.005 moles of HA from that solution. And our final volume, so once we add HA and A minus together, we're going to have 100 total milliliters or 0.1 liters. So our new concentration of HA is going to be 0.05, okay? And so we're doing the exact same math, the exact same addition to find A minus. So our buffer E is going to be 0.05 molar of HA and A minus. Now we need to make buffer F. So buffer F is made from buffer E. So we are going to be taking 10 mils of E and 90 mils of water to make a new 100 ml solution. So our initial concentration is 0.05. We're taking 10 mils, and we need to figure out what our new concentration is. So M1V1 equals M2V2. So 0.05 times 10 mils. So we're taking 10 mils of this solution to make a 100 ml solution. And that new concentration is 0.05, or 0.005. Okay, so we have one more solution to make. We have to make solution G. So solution G is going to be starting with this concentration. So you are going to be taking 10 mils of this guy to make 100 mils of G. So I will let you do that math on your own. It's going to be the same as this one, except your starting concentration is going to be this guy. Okay, so once we have all of our buffer solutions made, we are going to be taking the pH of them, and then we are going to be adding our titrants. So in this case, in part 2, we're going to start with solution E, and we are going to take 40 mils of E, or 0.04 liters, of our 0.05 molar solution. So in order to figure out how these guys are going to react, we need to convert them to moles. So we are starting with, when you multiply volume times concentration, you're going to get your moles. So we need to find out how many moles of HA and A minus we're starting with. So 0.04 liters times our 0.05 concentration gives us 0.002 moles. So in our ice table, we have our reaction. So HA plus H2O makes A minus and H3O plus. So we're starting with 0.002 moles of HA and 0.002 moles of A minus. Now we need to think about our titrant. So in our procedure, it says we're adding 2 mils of HCl. We know that dissociates 100%, so that means we're getting 100% H3O plus, okay? So 2 mils of H3O plus, or 0.002 liters. We know the concentration is 0.05. And that means we are reacting 0.0001 moles of H3O plus. So that is our initial concentration of H3O plus that we're adding. Now, we know since we're adding H3O plus, we're doing the reverse reaction. So all of our H3O plus, strong acid, is reacting with our conjugate base. So we're subtracting how much we're reacting with from our conjugate base, So this is reacting with this, and we're creating this. So we have to add that same amount over here because our HA and A minus are in a 1-to-1 molar ratio based on the equation. So 0.002 minus 0.0001 gives 0.0019. This addition gives you 0.0021. Well, now what do we do with this information? So what this means is that at equilibrium, our new equilibrium, we have this amount of conjugate base and this amount of our weak acid. So if we were to measure the pH of this new equilibrium, and we can put these values in here in that Henderson-Hasselbalch equation, we can solve for the pKa of this experiment. So this is experimental. So pH, the measured pH equals the experimental pKa plus the log of your conjugate base over weak acid. All right, so you might be thinking, this is in moles, this is in concentration. How can we simply substitute in moles instead of concentration? Well, these have the same volume. So volume divided by volume, the same volume equals 1. So we can just put in the moles here. Okay, so this is an acid situation. We are also reacting with strong base. So in that case, what we have is we're starting with the same concentration of 0.002 moles of E. So this is for E. You guys are going to have to redo these ice tables and calculations for F and for G. Okay, so for the basic conditions, we have a new equation. So when you react OHs, when you put OHs in a buffer system, it's going to react with the weak base. It's going to steal that proton from the weak base, or from the weak acid, to make water. And you're going to be left over with A minuses. So we are using the same volume and concentration of OH that we did of H pluses. So we have that same concentration. So in this case, our 0.0001 of OHs are reacting with 0.002 of this guy. So we're subtracting on this side. And everything that we're reacting here, we are creating A minuses. So we have to add on this side. So at equilibrium, 0.002 minus our OH concentration gives us a new equilibrium. And our 0.002, our initial, plus what we made using this guy, gives us 0.0021. So using the Henderson-Hasselbalch equation here, we're going to measure the pH of this reaction. We have the log of our concentrations, and we can solve for what pKa is experimentally. So we are going to be you will have to do this ice table and calculations again for F and G. Remember, the only difference is that the concentration is going to be diluted by a factor of 10 for G, and then another 10 for F and another 10 for G. Okay, so your top initial moles is going to be different. You're going to be adding the same amount of OH for all of them. Okay, so when we are thinking about the buffer capacity of these different buffer solutions that we're making, the buffer capacity is inversely proportional to the change in pH. And that should make sense, right? Because if your buffer system, when you add titrant, if the pH changes a lot, it's not a good buffer. If your pH only changes a little bit, that's a good buffer. So your buffer capacity is inversely proportional to pH, the change in pH, so it's the opposite. Another way to think about that is your buffer capacity is proportional to the formal concentration of your buffer. So what is your formal concentration of your buffer? That's going to be your concentration of HA plus your concentration of H minus. So if we are starting from a more concentrated solution, so buffer E, if it's more concentrated, these numbers are going to be bigger. So if these numbers are bigger, your buffer capacity is bigger. As you're diluting, your concentrations are getting smaller. So if that's directly proportional to your buffer capacity, beta, that means your buffer capacity is getting worse. So as you get more dilute, you should see a bigger pH change, and your buffer capacity should be going down. Okay, so before we start doing the walkthrough of the experiment, I want to mention about the lab report. So this experiment is being done the week of April 27th. So for my classes, that's Monday at 1 p.m. and Tuesday at 12:30 p.m. Your short lab report is due in 1 week. So what that means is the midnight before your next lab session. So just the same as normal, even during the shutdown. All right, so you are going to be writing an abstract. That's worth 25 points. So if you need guidance, please look at the lab report writing guide on the course library page. So our grading rubric is based on that. If you follow that to a T, you're gonna get 25 points. You need to do data and sample calcs. So when you are writing, we need tables 1, 2, and 3, okay? We also need the mean pKa, the mean Ka. We need sample calculations. What does that mean? Exactly what I have here. So we need to know how you made one of the buffers, how you diluted one of the buffers. We need we need an ice table for an acidic condition with the Henderson-Hasselbalch. We need one of the basic condition. Okay, those are two different things. So we need that. Okay, so the data section is going to be pretty big this time. Then we have discussion questions. As I'm going through the walkthrough, I will give you some hints. So the lab lecture should have also given you some hints. All right, let's get to it. Okay, so the first part of the experiment is making the buffer solutions. So we are going to start by making buffer E. So what we need to do is take 50 mils of HA, it's over here in A, and 50 mils of NaA. So I'm going to do that right now. There's one. Okay, so I have 50 mils of our HA, 50 mils of A minus. So I'm pouring that in here to make E. All right, I want to make an observation. So it smells like vinegar. So I'm going to assume that this might be acetic acid and sodium acetate. Okay, so we added HA plus Na minus, or Na plus A minus. So sodium acetate and acetic acid. All right, so hopefully at the end when we look up our experimental Ka, we'll find out that it's acetic acid. All right, so now that we have our buffer, our first buffer, we need to take 10 mils of E to make F. So 10 mils of E plus 90 mils of water. So we're gonna take one of these guys here, our 10 mil graduated cylinder. You wanna make sure you're at eye level. Okay. 10 mils. Pour that in. Okay. And our 90 mils. So this is a 50 mil grad cylinder, so we need to do 50 and then 40. All right, now we are going to an even more dilute solution, G. So we are taking 10 mils of F and putting it in G. All right, so I'm using the same little graduated cylinder. So this is a part where you might introduce some error. If there's any leftover E in our graduated cylinder. Alright, so now would be a good time, as you saw me struggle to get 10 mils exactly. What would be a better way to transfer more exact volumes? So think about that. So now I'm adding the 90 mils of water to this. So here's 50. And 40. Okay. So now we have E. I'm gonna give them each a little swirl. All right. So we have E, F, and G. So I haven't done anything to them yet. So we are going to read the pHs of just the buffer without adding any titrant to it. Okay, so this is our pH meter. It contains a little bulb here that will read the pH electronically for us. So you want to make sure that when you're using a pH meter, you want to keep it the bulb in a solution, a neutral solution of a pH of 7. You want to make sure that the bulb remains wet at all times, so the bulb is so it doesn't dry out. So currently, our pH reading is 7.08. So it's within the bounds of error. So if it was more than 0.1 off, we would have to recalibrate. But this is good enough for our purposes. So when you're thinking about error, also think about ways you can calibrate, etc. So now I'm going to read the pH of our E solution. Okay, so according to our pH meter, our pH is, come on,
Tara, what are we waiting for?
good question. So I'm just waiting for the pH meter to stabilize to try to get the most accurate reading. Alright, so it looks like 4.78 is our first measurement for E. Before I because this was at a pH of 4.78, I don't want to change the concentration of our solution here that the pH meter sits in. So I just have a beaker of water and I'm gonna just rinse it off real quick and then put it back in here. And I'm gonna just put that back. Okay, so our first pH reading for E. Amy, if you want to take a look at the table so I can point out where to look.
Yeah.
So our pH of E, our initial pH was 4.78. Okay, so that is our first reading. Now we are going to read the pH of F. So our pH meter, now that it's back in the its home solution, the pH meter reads 7.08 again. So what that means is the rinsing did its job and this solution is back to normal. Okay, it's back to its baseline. So now we are going to read F. Okay, so this one reads 4.86. So I'm gonna rinse that off, put it back in here. So 4.86. And now we need to read G. remember, G is our most dilute. So E was our most concentrated, F is diluted by 10, and G is diluted by 100. So our pH for our G solution is 5, right on the dot. So I'll rinse that off, put it back. All right, so 5.00. Okay, so our initial pHs are already changing with concentration. So you can see already that our pH is concentration dependent. So now what we're going to do is we are going to figure out how adding a little bit of HCl and a little bit of NaOH, how that will affect our pHs. So now what we're doing is we are taking 40 mils of our E. So we're going to do the acid reaction first. All right. So this is our E solution, and we want 40 mils. Okay. All right. E 40 mils, and we're done with that. And we want 2 mils of our 0.05 HCl. Too much. All right. Nice. Wait, that's 3.
We're having a little bit of trouble getting the right amount of HCl measured.
There we go. All right, so 2 mils of HCl. That was not ideal, but here we go. So we just added 2 mils of HCl to our 40 mils of our E solution. We'll give that a good swirl so it reacts. All right, so now we want to take the pH reading of this guy. All right, so what do we got? Press the measure button. All right, looks like 4.73. So our final pH is 4.73. So we can put that in this box here. And that's also our pH measured for our E plus HCl. So all of our initial pHs, 4.78, 4.86, 5.00. All right. So now we can do E plus NaOH. So again, we're going to take another 40 mils of our E solution. Okay. 40 mils of E. All right, I'm going to put NaOH in here. Okay. All right. E plus HCl. Okay. So, NaOH. Okay. So this will be much easier to pour from than the other guy. So this is our HCl. All right, so now we need 2 mils. So that's 2 mils exactly. So this is E plus 2 mils of our NaOH. Alright, so this is our orange minus. Okay. Alright, so our E plus our NaOH. So let's take this reading. Come on. So it looks like 4.83 is our reading. Rinse that off. All right. 4.83. I mean, .83. Okay. 86. 5.00. All right, so next we'll move on to F. All right, so we need 40 mils of F. Of HCl. Gonna take out a beaker this time. Okay. So our F plus HCl trial. It's a little too much. Come on, me. so a pipette would be ideal. Alright, I give up. Alright, so it's a tiny bit more than 2, but error. That's gonna be a source of error. Okay, so this is our HCl, so I'm gonna write a new sticky. Always label your labware. Oh. So those go together. Alright, so this is F plus HCl, so this is our more dilute solution. Alright, so what's our new reading for F? Alright, so F plus HCl should be more acidic, so the pH should be going down. And our new reading for F plus HCl is 4.36. So we're gonna write that in 2 places. So I already screwed up from before, so I'm just gonna do like that, 4.36. Get creative, guys. All right, 4.36. All right, so I input the moles, or the this is moles, this is not concentration. So these numbers, to convert back to concentration, you will divide this number and this number by 0.042. I'm just leaving them in moles because the volumes are the same. So concentration in moles essentially is the same in this case. Okay, so you guys will have to calculate the concentration for the new concentration of F at equilibrium using the ice tables. So that's where these come from, is the ice tables that we did during the lab lecture. So you guys will have to do that calculation to find the equilibrium concentrations of HA and A minus using the more dilute solutions in the ice table, okay? And then you can do the rest of the math using the Henderson-Hasselbalch equation. I am not going to do that for you. Okay, so let's do F plus, this was 8.3. Okay, so let's do F plus NaOH. So we're done with this guy. We have our F, we have our F plus NaOH beaker. So we need our 40 mils. Alright, so our 40 mils of F, we're done with EF now. And we need our OH minus. Nice. Okay, so 2 mils of NaOH. Alright. Put that to the side. We're going to swirl this up. You don't want to rely on Brownian motion here.
No.
Alright, so let's take take this reading. All right, and remember this is our more dilute solution. All right, and we added OH, so our pH should be going up because it's more basic now. So I'm just waiting for it to stabilize. Come on.
Or not.
Patience is key. Need some more swirling. All right, another source of experimental improvement would be maybe using like a stir bar and stirring it for a little while before you take pH. That might be a good one. All right, now it looks good. So we have 5.39. So F plus NaOH is, our pH rating was 5.39. So let's write that down. So we're going to write it in table 2, 5.39. Oops. 5.39. And then also here, 5.39. Okay, so our final experiment here is our most dilute solution G. So we're going to do our G plus HCl. So we need 40 mils of G. Try not to spill it on your hand like I just did. But this is why we wear gloves. Yes, right on the money. Alright, so our 40 mils of G. Just making a mess here. 40 mils of G, and we need 2 mils of HCl. Come on, HCl. Alright, HCl and I are in a fight. Alright, close enough. So, our 2 mils of HCl, it's just a little below 2, but close enough for our learning purposes. So now we're done with HCl. Alright, swirl this guy around. Gotta make sure this is back at its normal position, which it is. Swirl, swirl, swirl. Okay, now let's take this new reading. So G plus HCl is, yikes. All right, guys, we're in the 3s now. Okay, looks like 3.08 is our G plus HCl. So G went from 5 to 3.08. 3.08 there. Where are we? 3.08 here. All right. Now, we just need to get rid of that guy. All right, our last one, G plus NaOH. Let's get this bread, as the youngins say. All right. All right, 40 mils of G. And we need our 2 mils of NaOH. Nice. All right. So G, our most dilute solution, and NaOH. Let's see what we got. All right, so our last reading here is, yikes, yikes, yikes. We're all the way up in the 11s. Remember, we started at 5. So our final reading is still going up. All right, looks like, oh, nope, spoke too soon. 11.27. So we went from 5 to 11.27. Oh, no. 11.27. 11.27. All right, so now with these tables, you need to do delta pH. So delta pH is final minus initial. And then, right, if you're, based on what we learned in the lab lecture, your buffer capacity, so this B here is buffer capacity, is inversely proportional to your change in pH. So this guy only changes by 0.05. This guy changes by a factor of almost 2. So the smaller the pH change, this is the best buffer capacity. This one changes by the most, so this has the worst buffer capacity. So we're not looking for numbers here, we're just looking best to worst, okay? Same thing with table number 2, right? So our more concentrated guy only moves a little bit, so this one is, figure it out.
Use your brains.
Use your brains. All right, so now here, you need to do the ice table again to figure out what these concentrations are, or if you want to leave them in moles, whatever, okay? So then you need to figure out what the ratio of A minus over HA is, right? So then you need to take the log of that. And the negative log, remember, the negative log of this is your pKa. So you need to experimentally, based on your pHs, your log of your concentrations, using the Henderson-Hasselbalch equation, solve for pKa. All right, now you might be thinking, why is this blacked out? Well, figure out what your equilibrium concentrations are in your ice table, and that will give you a clue, okay? So that's also one of your discussion questions. All right, so I'm not going to give you too many hints about this. Think about it. There's a good reason why these are blacked out, so that's going to help you there. All right, so for question 1, it's asking about the formal concentration, okay? It gives you the formal concentration equation, so you are going to have to figure out what your formal concentrations are. And how does that relationship work with your delta pHs, okay, and your buffer capacities? So it says Sorry, low battery. Does the pH of a buffer before the addition of acid or base depend on its formal concentration? So this is talking about just table 1, right? So the formal concentration is this plus this gives you this pH. This plus this gives you this pH. This plus this gives you this pH. Are they the same or are they different? Is there a dependence here? Talk about it. All right. And then question number 2 is asking about the buffer capacities after. So this is talking about delta pH. Question 3 is the longest question. Okay, so this directly tells you, for question number 3, that trials G with acid and base, was the buffer solution destroyed by the addition of acid or base? Okay, so remember from the plot of a buffer, right, it looks like this, and the buffer region is in the level part. And when you add too much acid or base, right, you don't have a buffer anymore because the buffer region means it's resisting pH. So it's essentially asking, is it still resisting pH? If it's not, then that much is destroying your buffer. If it is resisting pH, then you would see the pH still be about 4 point something. Okay, so you need to talk about, for this one, make sure to answer each part of the question. So when it says rationalize your results, we want you to talk about the theory of the buffer. So what we went over, what a buffer is, okay? And also back it up by what you saw experimentally. Okay. And question number 4 is basically a summary. So we essentially want you to write a summary here. So summarize your results, the conclusion you made about this buffer system, and then report any errors. So as we went through, I explicitly said what some of the errors were. All right, so that concludes this experiment. So I am going to now pour all of these guys into the waste beaker, rinse them out, and return the supplies to their rightful lab stations. And make sure that this guy is back in its pH 7 solution. Okay, so if you have any questions, make sure to email your TA. If anything wasn't clear, they can answer all of your questions. My name is Tara Mooney. If you need to email me regarding any steps that I did, feel free to do so. All right, enjoy.